Okay, so yeah, let's see. Real quick before we get into the math, I want to remind everybody about the first homework set due date, which is today, right? And notice all homework due times are 11 p.m. Durham time, that is. So you do still have, what's that? Nearly 11 hours to get that turned in. But anyway, just a quick reminder there. Okay, and now proceeding with where we left off in the material last time. We're going to do flashbacks to a couple of linear algebra theorems. I say may have seen. I don't know for sure what your section of Math 218 necessarily covered. But so either way, here's the theorem. Two of them. We'll start with the first one. So this concerns a list. And we talked about lists last time, right? So a list is not the same as a set. The idea here is this is two vectors, but furthermore, in addition to that, there is the order that they are in, right? A is first in this particular list. B is second, right? So that's an important characteristic of a list. Okay, so given a list, we're going to do the following. First vector, second vector. All right, again, the order matters. I'll just leave that. First thing we're going to do is we're going to make a matrix out of the list by making the first vector the first column, second vector the second column. Given the matrix, we're going to define a linear transformation. Now, that's in the usual way, right? Given a matrix, you can interpret as a linear transformation like so. And that gives us this linear transformation here like this. So the list gives the matrix, which then gives the linear transformation. Okay. That linear transformation, then, I can ask the question, okay, well, what would happen if I were to take all the points in the unit square here in the domain, right? And if I were to take all those points, plug them into the linear transformation, see what comes out, and what would come out would be, well, it'd be a parallelogram, of course. And this is then the last player in our game. So this is parallelogram I'm going to go ahead and outline in purple as well. Okay, so the list creates a matrix, which creates a linear transformation, which creates a parallelogram. All right, everybody with me so far? So here's a little subtlety, and by the way, I still haven't gotten to the statement of the theorem yet. This is all just the setup about which we will make a statement, right? But I am going to observe, check this out. If I were to look at, okay, what is the image of this bottom edge of the unit square? Namely, if I were to look over here at, this edge, what is that? Well, if you think about it, that is the image of the first standard basis vector. Where have I heard that phrase before? The image of a standard basis vector. That means it came from the corresponding column of the matrix, which means it was the first vector in the list, which means it's the A vector, as I already have it labeled there. Right? And then likewise, if I look at the, what is the image of that edge? That's, of course, this edge. That's the image of the second standard basis vector, second column, therefore, second vector in the list. Okay, so again, I haven't really done anything yet. I just set some things up, right? Made an observation about what the edges of the parallelogram are. Yeah?
The green line on the right and the green line on the left are not equal, right? Because
certainly.
Undergone a transformation of the T.
Yeah. That's right. Yeah. So this is color catastrophe. This is the E1 vector. This is T of the E1 vector. That's right. Yeah. Okay. So here's the first part of the statement. First part of the statement is that the determinant. Let's see if I can highlight. So the determinant of that matrix. Now, not the determinant by itself. The absolute value of that determinant will give you the area of that parallelogram. And that's an eyebrow raiser, right? That's weird. What? Wait a second. Determinant is defined with algebra. It's defined with a formula, which, by the way, a really simple formula, right? Determinant of a 2x2 matrix, 3-function arithmetic. add, subtract, multiply. It's not even any division, right? It's very simple formula for determinant. And yet it's telling you this area over here, which involves, you'd think some trig, because there's an angle involved. Shouldn't I have to take like the sine of that angle or something? Oh, magnitude of the edge vector. Doesn't that involve a square root? Where's the square roots? Where's the trig? Why is it 3-function arithmetic? Absolute value of the determinant. It seems too good to be true. Mysteriously, still true. All right, so that's the first part of the theorem. Quick question. I just want to take stock of where we are. How many people have seen this fact before about determinants? Okay, good. All right. Here's the second fact. Also really surprising, I think, and I'm going to have to zoom out to get this to fit on the page. So the magnitude of the determinant tells us something, namely the area. What about the sign of the determinant? What does, the determinant being plus or minus, what does that mean? And I claim that it tells us about the order of the list. Again, keep in mind, this all came from a list initially, A first, B second. And so, looking at our picture here, and let's just start with the first case. If the determinant is positive, easily computed determinant, right? Again, easy formula. If the determinant's positive, that means that the list is counterclockwise, such as, for example, as I have it drawn in that picture right there. So what I think is really amazing about both of these results, both the absolute value giving you the area and the sign giving you the order, is in both cases we have something defined purely algebraically, giving us results that are intrinsically geometric. And that's pretty unexpected, right? So really interesting when stuff like that happens. Okay, now there's some other stuff on here about the plane not being inverted, order being preserved. It's not exactly clear what I mean by that. I'm going to come back to that in just a moment. I think it's easier to understand that point if I start effectively with the next case. Let's consider what happens when the determinant is negative. Okay, so determinant being negative. Well, it says here that AB is clockwise, and before I can go any further, I have to recognize that now my picture is not accurate. The picture that I drew here, that I was sitting right there looking at, is clearly counterclockwise. But in the case that we're considering here, I need AB to be clockwise. So I am going to change my picture for that purpose. Let's see here. I guess I can leave all of that. And I'm going to come over here. I'm going to come over here, and real quick, I'm going to white out. That's no longer going to be the B vector, and this is no longer going to be the A vector. So I need for this now to be the, oh, come on. I need for that to be the A vector, and for this to be the B vector. Okay, all right. Now, with that change made to the picture, and again, I have to zoom out to fit it all on here. Determinant being negative means AB is clockwise, appropriate to the edit that I've made to the picture here now. A first, B second, right? It goes now clockwise. So now let me tell you what I mean by when I say that that the plane is inverted and the orders are reversed. We're talking about the linear transformation. We're talking about what the linear transformation does. And let's start with talking about orders. I claim that the orders got reversed here. And what I mean by that is what is intrinsically a counterclockwise order, E1 to E2, by way of the transformation, that has now been turned into a clockwise order from T of E1 to T of E2. And let's just think now, how could that be, right? I mean, what do linear transformations do? They take the plane, they might stretch, they might rotate, right? They might shear, right? There's various things that a linear transformation can do, but all of those things, magnifications, right? That all of those things preserve order. If you have a counterclockwise order, and if you kind of just stretch, it's going to keep it counterclockwise, right? That's not going to change that fact. What is it that could possibly make a counterclockwise turn into a clockwise? And there's really only one answer. And that is the linear transformation must flip it over. There's got to be some sort of a flipping it upside down. Or you could think of it alternatively as mirror imaging, morally equivalent to flipping it over, right? Different metaphor, but same result. Something along that line. So I use the word inverted here as a kind of a catch-all to represent effectively flipping it upside down. And that is kind of an unavoidable consequence of the fact that the orders were reversed. Is everybody with me? So now I can go back to the positive determinant case, and I'm not going to redraw the picture, right? But determinant positive means counterclockwise. Well, E1, E2 was counterclockwise, so the orders are preserved, and there was no flip. Okay. All right. How are we doing? Okay. All right. Third case, the kind of the annoying, unlikely but possible scenario. If the determinant is 0, well, then that tells us that the A comma B is dependent. Again, keep in mind that's our third case of ordering that's neither clockwise nor counterclockwise. And if you think about it, if A and B are dependent means that they're either parallel or one is 0 or they're both 0. And in all of those cases, if you were to draw what that looks like, what the linear transformation is doing is there's going to be some sort of a smushing or squishing. The image of the linear transformation won't be two-dimensional. The matrix is singular. Y'all remember singularity? Yeah. Okay. All right. So, remarkable theorem that determinant, let's see here, let me do like this. The determinant, the purely algebraically defined object on the matrix, gives you shockingly meaningful results about purely geometric results about the parallelogram and the linear transformation that created it. That's pretty wild. Okay, so there's a three-dimensional version of this. I'm going to go quickly through the three-dimensional version because it's the same thing, just one dimension up. In fact, I would bet dollars to donuts that if I were to charge you with the task of speculating what a three-dimensional version of this theorem would be, you would speculate exactly what I'm about to write down. And that is that when you have a list that creates a matrix, which creates a linear transformation, which creates now a three-dimensional version of a parallelogram. We call it a parallelepiped, right? And you can persuade yourself, thinking about edges and all that these edges are A, B, and C, namely the exact three vectors that we started with here. This is all shameless rip-offs of what we just saw two-dimensionally. And we get all the analogous results. The absolute value of the determinant tells you, well, it's not going to give you the area of a three-dimensional thing. The three-dimensional things aren't about area, right? They're about volume. So it gives you the volume of that parallelepiped. Don't forget to take the absolute value. By the way, real quick, just a comment. In theory, you already know this, but I just want to double check. This word here, volume, is an intrinsically positive thing. Volume means positive, but non-negative. Right? There's no such thing as a negative volume. Right? Likewise, there is no such thing as a negative area. Area is an intrinsically positive thing. And continuing the analogy, distance, intrinsically positive. Right? Naturally positive thing. Okay, so the absolute value gives you the volume, and the sign tells you about the order. in totally analogous ways. So, for example, positive corresponds to right-hand order. Now, keep in mind we've got these columns, aka these vectors. We've got this list of 3 vectors, and right-hand order means, this whole thing, right? Y'all remember the right-hand gesture, the hand signal from last time. So, and if you think about it, of course, these standard basis vectors are, of course, always right-hand order. And so what we've got here, if that's always right-hand order, and if this list ends up being right-hand order, then the order is preserved. And so nothing got, there isn't, what is the 3-dimensional version of flipping something over? It's harder to imagine, right? But it's easier to imagine sort of mirror imaging or inverting through a line, or however you want to say it. So none of that nonsense is happening in this picture, because right hands turned into right hands, right? On the other hand, no pun intended, if the determinant's negative, that means this is a left-hand order, which means that there is a reversal of orders, which means that there's a reflection of some sort happening in that transformation. Okay. All right. And again, the annoying third case, determinant being 0 means it's a singular matrix, which means there's squishing going on, which means that these 3 vectors they're some sort of linearly dependent. Maybe one of them is 0, maybe 2 of them are parallel, maybe one's a combination of the others, whatever, but they're dependent. Okay. All right, so I think it's lovely to dwell on how this theorem and this theorem are morally I'm going to say morally equivalent, but they're highly analogous. You would expect the latter from the former, and they're also true. Okay, so now with that background, I'm going to get into defining cross product finally. I know we've been in this section for a while already, but I like to have all of the tools ready to be discussed when we do finally get around to talking about cross product. Here's the definition of cross product. This is specifically the cross product of 2 vectors in R3. What I'm defining here is a peculiarity of R3. R3 is the only Euclidean space in which you can define a cross product of 2 vectors. Right now, y'all saw that homework exercise where you define a generalization of this if you have n-1 vectors in Rn. Yeah, sure, okay, fine, but that's not a binary operation. We tend to think of a product as being something where there's 2. There's the thing on the left and the thing on the right. Right, it's a binary operation. So binary means there's only 2 of them. 2 of them means we're stuck in R3. Okay, so here's the formula. Arbitrary looking formula. Just a definition. But it's a definition that ends up being very, very conveniently chosen. It has some really unexpected nice properties that we're going to start seeing here. So the first one I'm going to point out is that seemingly weird arbitrary formula, very closely connected to determinants. Now, this is just a computation. This is just plug and chug. Let me do part of the plug and chug for you. Let's talk about where this came from. Right? Well, if I take this determinant the old-fashioned way, right, and I go across the top row and all of that business, you cross out the row and column. Y'all remember all that. What I end up with is this times the determinant of this 2 by 2 minor. Well, that gives me A2B3 minus A3B2 apparently in the first entry, because that's what's being multiplied by E1. Is that cool? Likewise for the other terms. Don't forget your minus sign. Don't forget that there's when you do determinants, there's a whole plus, minus, plus pattern as you go across, right? So you've got to be careful with that. I am well aware that I could have absorbed that minus sign into this formula. Arguably would have been simpler looking if I had written that minus sign absorbed in there. I like to leave it visible, if only as a reminder. Okay. All right. Now, question of curiosity. How many people have seen this formula before? Show hands. Okay. Half-ish. Okay. No worries. There is something uncomfortable about this formula. Determinant, as we've defined it previously, applies only to a matrix. A matrix, as we have seen them previously, requires that the elements be numbers. Wait a minute. What's up with that? Right? You've got a vector in the place of where a number should be. Can you do that? Is that okay? What does that even mean? Worrisome questions. Right? So we're not going to worry about that at all. I'm just going to say that, okay, technically when I say determinant, technically, all right, let's confess it isn't really quite, because this thing isn't really a matrix, because those things aren't numbers as they're supposed to be, right? So don't worry about whether this is an actual determinant. We call it a symbolic determinant in the sense that, we're just going to compute blindly from the formula for determinant, just as a kind of a bookkeeping convenience, rather than having to write all of this down, right? It's just a little bit more convenient and organized seeming to write that down. So, is that cool? Everybody all right? Okay. Yeah. Whoops. Here we go. All right. Now, here's another fact. I'm going to take a dot product with the cross product. Now this seems like a strange thing to do, but let me first recognize this cross product. There it is, right? There's that cross product. And if I were to take some vector C with certain coordinates, C1, C2, C3, and if I were to do this dot product here, as written, you can multiply that all out, and interestingly, what you get is that dot product is this actual, no kidding, determinant. And that's a little surprising. It's not hard to see it happen. It's just a matter of kind of multiplying it out. I mean, let's just, for example, in this dot product, I'm going to have that times that. Well, that's that times the determinant of that. You can kind of see in the process of working out that dot product, you're literally going to be reproducing the algebra of a determinant. So no surprise once you sort of see that, and, et cetera for the other terms. But still kind of a weird, it's interesting that these pieces kind of dovetailed together so well, mysteriously. Is everybody happy? All right. Case could be made that maybe this is why we defined cross product with this formula in the first place. Right? This gives us exactly the thing that allows us to turn a dot product into a determinant. Okay. So anyway, here's the result is that this expression called a triple product is a determinant. And case could be made, you kind of don't even really need the term triple product because we already have a term, determinant. Right? They're literally the same expression. Exactly the same. Right? Triple products are determinants. The only reason we actually have different words is because determinant is understood to be something that acts on a matrix. And a list of three vectors is, it's easy to turn it into a matrix, but it itself is technically not a matrix. So, we need a different word there. Is that cool? All right, now let me tell you why this formula is important, and I should not have erased the, whoopsie. All right, let me be more careful here. Tell you why this formula here is important. This is going to be a really important tool in understanding cross products for the following reason. We're trying to understand cross products, but we already understand dot products and we already understand determinants. So really valuable tool here that if you want to understand something, connect it to things that you already understand. When you connect the unknown to the known, then you can draw inferences in various clever ways, and then we're going to see that play out over the next few pages here. All right, so that's why I like to start with this formula. Okay, now I'm going to remind you that sadly I have to make tough choices about what to spend time on, and there's a bunch of results that we're going to talk about in the rest of this, the rest of these notes on this book section. All of the results, there's a corresponding proof. And they're lovely proofs. They're really kind of beautiful. And we don't have time for them. So I am not going to talk through most of these proofs. I am going to do this first one because I just want to whet your appetite. I want to persuade you this is pretty cool, right? And I want you to see a glimpse of how many different sort of connections and mysteriously convenient opportunities for argument there are in this sort of area of the course. But we just don't have time to go through all of the arguments themselves. So what I'm going to do is, again, I'm going to go through one. I'm going to encourage you all to go through the rest. You don't have to. It's not testable material. Is that what you were going to ask? No.
Where would we find the?
Oh, right here in the notes.
Okay.
Right here in the notes. I'm just gonna gloss over them mostly, but yeah. So read them if you like. By the way, the book, of course, has different takes on not only how to prove all these results that I'm going to present, but how to order them and which what path to take through this particular collection of ideas. So very different presentation in the book. I encourage you to look at both. I think you're going to like mine better. I'm biased. Maybe you'll like the books better. It doesn't matter. Okay, so here we go. First fact. The cross product is always orthogonal to both of the input vectors. It's always orthogonal to both of the input vectors. Really surprising fact. Also, one of the sort of, motivating, why would I ever care about this weirdly defined cross product? Well, because it's a way to generate a vector that's perpendicular to two given inputs. And this is something that comes up where, I've got these two vectors. I need to find something perpendicular to it. Boom. Cool. Right? Cross product. All right. Now, how do we prove orthogonality? Well, we prove orthogonality by taking the dot product and confirming that we get 0. That's the definition of orthogonality. Dot product is 0. Okay. All right, so that is, look, you can crank that out. I mean, we've got a formula for cross product. We've got a formula for dot product. Take a deep breath, write it all down, collect the terms. What you're going to find is this massive cancellation and okay, confirmed, you will get 0, and you will also be left kind of, I don't know why. Like, it's very opaque, right? There's no sort of aha moment in the calculation itself. It just kind of is that it works out. So I consider that to be a disappointing argument to make to prove that orthogonality. Let me show you what I think is the cool argument. And that is, I'm going to compute this dot product by interpreting it as a triple product, which technically is, right? I'm doing a dot product. One of the vectors is a cross product. Dot product with a cross product is a triple product, which we just saw above is a determinant. Okay. Well, wait a minute. The determinant I can compute this determinant a couple of different ways. On the one hand, you could just observe, well, yeah, these two rows are the same, and Math218 tells us that when two rows are the same, the determinant's 0. So, boom, there's one point of view. But even more geometrically satisfying than that, I can interpret that determinant as a volume. First row gives me the first edge vector. Second row gives me the second edge vector, same exact vector. And then third row gives me the third vector. And all together, this defines, this defines a parallelepiped, which you can just draw out, and it's flat. These three vectors, right, if two of the vectors are the same, right, it gives you a flat parallelepiped. And so now I can argue from a geometric point of view, there's no volume in here. That volume is 0. Visually. Because the volume is 0, that means that the determinant is 0, that means that the triple product is 0, that means that the dot product is 0, and that's the definition of orthogonality. So this is what I like to call a high-level and I think very satisfying argument as to why cross products are orthogonal to their inputs. It's because we're connecting high-level ideas, dot product, triple product, determinant, volume, and then just making innocent geometric observation. Boom, we're done. So I love this kind of thing. All the the proofs that we're going to be skipping in this section today, they're all kind of this kind of thing. Okay, you're not responsible for those proofs, though. Okay, next fact. And for the remainder, I'm just going to state the facts. I'm not going to go through the proofs. You're not responsible for them. Wish we had time. It's just don't have the time. You can cycle triple products, and you get the same thing. Nothing changes. It's a very surprising fact. Let me clarify what I mean by cycle. What had been in the third position goes to the second position. What had been in the second position goes to the first position. What had been in the first position goes over to the third position, right? So that's just, sort of cycling, I think, is a natural word there. And so ABC turns into BCA, which turns into CAB. So when you cycle like that, those triple products are always equal. Now again, for your own personal interest, I think it'd be a great idea to think through the details that I've outlined in the argument here. I think it's rewarding. We don't have time for that, and you don't technically have to, but it'd be a good study tool if you're looking for that. Okay, next. This is my favorite one. It's so cool. The magnitude of the cross product always gives you the area of the resulting parallelogram. Now, another really surprising thing, right? Why would area equal to a magnitude? Why would area equal distance? They don't even have the same units. This is unexpected for sure, right? But shockingly, it's true. Now, I'm going to call your attention to a couple of notational things here. I like this notation. I don't remember where I got this notation from. It's likely that I saw this decades ago, forgot that I saw it, and then accidentally reinvented it. Much less likely, but I can't eliminate the possibility I may have invented it. I don't think so. But anyway, it's very natural notation. What this means is the parallel lines here mean parallelo something, right? And when there's two vectors listed, then that just means that we look at those two vectors, right? And the two parallel lines tell me that, I'm looking for the parallelogram in this case that's defined by those two vectors. Does everybody buy it? Everybody see the notation there? Yeah. Okay. Yeah, question.
So, does that mean you can, if you have a parallelogram made up of two vectors, you can always find an orthogonal vector?
Oh, sure. Well, now that's always true. Yeah. And I'm going to give you a proof by picture on that. I mean, two vectors, whatever your two vectors are, they define a plane. And once you have a plane, there's always a vector perpendicular to that plane. Yeah. Does that make sense?
Yes.
Yeah. But yes, totally. Yep. Right. Okay. Likewise with the notation, you'll see here I've used it again, but here I've used it in reference to three vectors. This refers to a parallelepiped where the vectors are, well, let's see, that and this and this. And so this notation refers to this parallelepiped, solid parallelepiped there. Okay. All right, just notation. So give this argument a look-see if you're so inclined. I think it's a fantastic little bit of what I like to call mathematical weightlifting. It's exercise in using and connecting some of the objects, tools and connections that we've already made between these ideas. And whenever you take new ideas and use them, right, then you're building some mathematical muscles there. You're getting more used to the ideas. You're getting practice with using the ideas. Okay. So give that a look, I hope, anyway. Continuing. If the cross product is 0, that means that the pair is linearly dependent. Now, why is that? Well, again, there's good reasons. I think this is a nice little argument here. Again, I'm just giving you the outline. You can fill in the details. Again, I think it's good practice. You don't have to know the proof, but you do need to make sure that you understand and retain this result. Okay, here's a really nice one. This ordered list, keep in mind, when you're talking about an ordered list, the order really is important. So first vector, second vector, and then the third vector is the cross product, where specifically the first one is the first vector in the cross product, and the second one is the second vector in the cross product. That's critical. Right? So noted that list, I'm going to say it sloppily first, just for sort of eloquence. It's in right-hand order. Right-hand ordered list. Okay, all right. Now let me not be sloppy. Technically, one of these vectors could be 0. If one of these vectors is 0, then, well, it's not either technically right-hand or left-hand. So I can't technically say that it's always right-hand order. What I can say is that it is never in left-hand order. And that's always true. So, unless one of these three vectors is 0, it's in right-hand order. Okay. All right. Again, cool proof. Again, we don't have time. Again, I encourage you to take a look. Again, you don't have to. Okay, so I claim we actually now have, you will have noticed, lots of geometric properties of the cross product. In fact, we have so many geometric properties of the cross product now that we have, in fact, a purely geometric description. We can actually make this a definition. In fact, our textbook does. This is the definition, the starting point of the conversation for the textbook for what a cross product is. The cross product, A cross B, is the unique vector that has these three properties. It's the unique vector that is orthogonal to both inputs, whose magnitude gives you the area, and that's never a left-hand listing. That never makes this a left-hand listing. So there is always exactly one such vector satisfying these properties. That is the book's definition of a cross product. Now, Again, why does the book define it that way? I define cross product this way. Pros and cons. I think if you look at the book's full presentation, I think you'll find it gets pretty hairy in several places. So that's why I like mine better. We have to make a couple of slick algebraic observations, but this isn't what I would... To me, this is not hairy. To me, this is just carefully set up and organized. And once you make that one sort of, delicate algebraic, pair of delicate algebraic observations, then everything else is just clever applications, clever connections, and practically zero algebra. Zero pain algebra anyway, for the rest of the arguments. So I like that one. Okay. All right. Just a few more things I want to mention. It is tempting to think back to elementary school when you define times the first time. And, of course, one of the first things they tell you about multiplication is you can do it in either order. 4 times 7 is 7 times 4. Either way, knock yourself out, right? Commutativity is the big word that they throw at you at some point. Scalar multiplication is commutative. Dot products are commutative. Cross products are not. And it's just, it's sad, but it's unavoidably the case. You get a minus sign here now. So be really careful when you're doing algebra with cross products. Don't just whip commutativity around like it's free. It's not. Right? Got to be careful with this. Okay, the book leaves out a couple of facts that I think are worth mentioning. There is a linearity involved. Now, y'all actually already proved this as a homework exercise. I say already. You will have by 11 p.m. tonight, in the next 10 hours, if not already, shown that this is a linear transformation. So anyway, I think it's nice to just point that out and interpret it as just a statement about algebra. We have a kind of distributivity and associativity as a result of linearity. Right? So linearity is a property of a function. Distributivity and associativity are properties of an operation. So I like to phrase it in those terms. All right. And it goes on either side. That's also nice to observe. Next, just another sort of landmine to be on the lookout for. We're accustomed to being able to move parentheses around to our heart's content. This is the associativity property of multiplication. We remember this from scalars, right? Scalar multiplication is associative. And there are plenty of other associativities in multiplication-like operations that y'all have seen in the past. Cross product doesn't. So again, heads up, don't play fast and loose with parentheses, with cross products involved. Okay, couple of quick applications. I'm not going to get off into physics here. Again, that's not the purpose of this course, but I just think it's interesting to recognize where it does come up. So if you have an axis here, and maybe you've got maybe this is the axle of a car or something like that, and something that's going to be turning, right? And if you push, from some point here that we imagine as being connected to that axle, if you push on it with a force in such a way that, well, of course, that would make the axle start to turn. This creates something called torque. Torque is kind of like force. It's not the same as force. Just a quick appeal. You could imagine, again, if I had an arm sticking out of an axle like that. If I were to grab it right here and push, you could imagine that might turn the axle. You could imagine, however, though, instead, that if you were to get real close and then push, it's going to be a lot harder to turn that axle. right? You just don't have, I don't know if you've ever tried to, if there's a bolt that's, holding something down, screwed in, all the way down bolt, try to grab it with your fingers and unscrew it. It's really hard, right? But if you put a wrench on there, effectively what you're doing is you're lengthening your arm. You're increasing the magnitude of that R in purple there. And then it's no problem to turn it. Okay. All right. So anyway, cross product is how you compute torque. So that's a kind of a mechanical example. Then there's a magnetic field example. This is weird. Magnetic fields are strange. By the way, don't ask me why this is true. Nobody knows why. This is just empirically that, right? We know that it's true. Nobody knows why it's true, right? But here's the thing. It just happens to be. If you've got a magnetic field, and notice I've got the magnetic field pointing like so, right? If you move a charged particle through a magnetic field and take the cross product, V cross B, so V, the velocity, first vector, the B for the magnetic field, second vector, that cross product tells you the direction of the force that the magnetic field applies to that moving charged particle. Weird. Right? Charged particle can sit there in a magnetic field motionless and nothing happens. The magnetic field doesn't do anything to a still charged particle. But once it starts moving, then the magnetic field applies a force. So, very weird. All right. And again, cross product. How we doing? Everybody with me? Okay, so moving on, section 1.5, we're talking about equations of planes and related matters. So first, let's get the equation for a plane done. This is a straightforward little calculation. But let's suppose that I have a plane given, and let's see here. I will define the plane by way of a point that's in the plane. And a vector in that is perpendicular to the plane. Let's take a moment to recognize that uniquely characterizes a plane, right? If you give me a point in it and a vector perpendicular to it, there is nothing left to talk about. There's no more ambiguities. There's only one such plane. Yeah? It makes sense geometrically? Yep.
Can that point be on the vector? Or they have to be two separate entities?
So I hear where you're coming from, but here, let me remind you, vectors don't have locations. Right? So, yeah. So no, I get where you're coming from, but just keep in mind, when I say a vector, you should always think, basically a whole family of arrows like this. And so there is no such thing as a point being on the entire family, right? It's always on some of those arrows, but yes, yeah. Is that satisfying?
Yes.
Cool. Good. All right. Okay, so with that defined, I want to find the equation. Keep in mind what an equation is. An equation is a point tester, right? So when I say I want to find the equation, what I mean is I want an algebraic test where I can just plug in an x, y, z, and what I will get is either a yay or a nay as to whether the point is or is not on the plane. Okay. So here's what I propose. An easy test, again, supposing that we are given the x naught, we are given the n. If I've got a point x, and if that point x is on the plane, well, wait a minute. If the x is on the plane, don't forget x naught was defined. It's the defining point on the plane. And so x being in the plane tells me that this difference, x minus x naught, is parallel to the plane. Everybody buy that? And here's the thing about that. If x minus x naught is parallel to the plane, then, color choices. That means that it is perpendicular to the normal vector. Okay, now look, I just committed the oops. Orthogonal, not perpendicular. If x minus x naught is 0, still cool, right? So I should have said orthogonal, not perpendicular. Everybody happy with that? Okay. All right. And check it out. That's an algebraic test. Right? So this is a lovely argument because it starts with a geometric assumption about a point being in a plane. That's all geometric. And it ends with an algebraic thing, namely that a certain set of coordinates satisfies a certain equation. Okay. All right, so there's your equation for a plane. And very often we kind of distribute and move terms around just for kind of aesthetics. Right? I think it kind of rolls off the tongue a little better as n dot x equals n dot x naught. I don't know. You don't have to. It doesn't matter. They're the same. They're totally equivalent. And now you can also, let's presume that this normal vector has coordinates a, b, and c. Well, if the normal vector has coordinates a, b, and c, then you can just crank out the dot product. If your x vector, as usual, has coordinates x, y, z, right? N dot x is, well, it's ax plus by plus cz. The right side, n is a given, and x naught is a given, so this dot product is just some given, well, it's not technically given, an easily computable constant, right, independent of x, y, z, so we'll just call that d. And so here is yet another alternative form of the equation of a plane. You can think of ax plus by plus cz equals d. Everybody see how I did that? Okay. All right, so a couple of slick observations to make about this, and let's look now at our two equations. There's this one and there's this one. Nice thing about the bottom equation is that you can just see right there what your normal vector is. Right there in the equation. You just pull those coefficients right off of the equation, and that gives you a vector that apparently is the normal vector that we used. So that's really nice, right? Just you can read it straight off of the equation. Very cool. Okay. All right. Now here's the next observation I want to make, and this is just what is this? Vaguely philosophical. Which of these equations should you like better? And they're both good. They both have their moments. But for my money, I like this one up here better. I think that's the better one. And let me explain why. Everything that's in this equation here is geometrically natural and meaningful. In normal vector. That means something geometrically. X naught, given point in the plane. That's geometrically meaningful. Right? X is the point that we're testing. Everything that you see there is something that has a natural meaning by itself intrinsically. You can't really say that about this bottom equation down here. What is B by itself? It's related to something meaningful. It's one of the coordinates of something meaningful. By itself, it's not really a thing. So I don't know. Something I want y'all to think about as we move through the material is that you want to distinguish between formulas that are good for plugging and chugging, which of course we do have to do sometimes, and that's I don't want to trash that completely, right? So yes, sure, that is computationally convenient and it has its moments. But remember that one of the important things about what we're doing in this course is we're talking about ideas, connecting ideas, using ideas to come up with new ideas, right? This is a course about ideas. And this version of the equation is the one where the ideas are most visibly present. This is the version that's going to be the most useful when you're trying to connect equations of planes to something else that's involved in the question or whatever. So really, this is what I would propose should be your primary instinct, as this is the equation of the plane. And of course, notice it's really easy to just convert. If you want to do a plug and chug, fine. You just multiply it out, nothing to it. Right? So, for your consideration, here's a different point of view on the same thing. Students have a strong tendency toward scalars and variables and coordinates because you're accustomed to it, right? But vectors are powerful tools. Vectors are the important players, the new sort of like the new fundamentally natural objects under discussion here. And so try to be drawn towards, not repulsed away from, try to be drawn towards equations that are written in terms of vectors, because that's natural. Okay. All right. Philosophy speech over. Okay, so let's do one. Let's find the equation of a plane. We are given in this question 3 points. Can reasonably ask, what is this plane? Let's see here, color choices. I'll use purple. The plane containing those 3 points, right? If you have 3 points, as long as they're not, along a single line or something annoying like that. 3 points generically defines a plane. Right? How do you find the equation of that plane? So here's the trick. There's always a trick when you're doing questions with lines and planes. It's very often this trick. But the big trick I'm going to point to is that if you have 2 points in a plane, then their difference is parallel to the plane. And then here again, that one also parallel to the plane. So 3 points in a plane gives you 2 independent vectors parallel to the plane. Okay, now once you have 2 vectors parallel to the plane, keep in mind what I'm looking for. I'm looking for a vector perpendicular to the plane. I have 2 parallel. I want one perpendicular, and this is one of the applications that we talked about of cross product. Cross product is the thing that allows you to find a vector perpendicular to 2 given inputs. That's exactly where we are here, right? So we want to find something that's perpendicular to both of those green vectors. Cross product does it for us. Everybody happy? Okay. And, of course, now it's all over but the shouting. Keep in mind, here's our equation for the plane up here. N dot x equals n dot x naught. And we just got through finding n. Let's see here. X naught. What are we going to use as our x naught? What is x? X naught. X naught's a point in the plane. We've got 3 of them. Take your pick. I personally have a preference between these 3 options, and that is I like small, easy numbers. So I'm going to pick this one here because it's got a 0. I love zeros, right? And the other numbers are relatively easy as well. So out of pure laziness, I pick A. But if you want to do B or C, totally fine, doesn't matter. Cool. And then there's your equation for your plane. How do you feel about all that? Everybody happy? Okay. Real quick, I'm going to point out, just for your strategic use, that notice in this argument that I gave here, I drew a picture. Right? I'm a big believer. I think you should always draw a picture when you have one of these kind of lines and planes geometry problems. because it just really helps to see what these things are that you have and how they, therefore, the picture might tell you how they relate to the things that you need, right? And so just invaluable to have a picture, so don't deprive yourself of that convenient tool. All right. Went along. Okay. This next observation is not in the book, but I think it's really, really handy. It's going to come up later in different ways. If you have an equation for a plane, and suppose there's no y's in the equation, let's just say. Right, so now real quick, what would that look like? Here again, here's the equation of a plane. If there's no y's in the equation, that would mean that you have something times x plus something times z equals d. No y, there's just no y's in there, right? So if that happens, let me say that differently. If algebraically you notice that that's the case, what does that mean geometrically? Right. Here's another common theme that you're going to notice in this class is we're always looking for and developing connections between algebra and geometry, right? So if algebraically you notice this, what geometric goodie do you get out of the deal? Right. And the answer is, if there's no y's in the equation, then your plane is parallel to the y-axis. That's a geometric statement. How about that? Right? Nice, powerful geometric conclusion with practically zero cost. All we have to do is just observe, check it out. I don't see any y's in there, right? It didn't even have to do algebra for that, right? If you just see that in the algebra. Yes?
I'm a little confused by the idea of a plane being parallel to a line.
Oh, yeah, sure. But, so if they don't intersect, right? If you have a plane like this, most of the time you expect a line eventually to intersect the plane, right? But you could have a line that just kind of cruises at a sort of a constant altitude above that plane and never intersects it. That's what we mean by parallel. Does that make sense? Yeah. Right. Anybody else? Is everybody happy?
So can it also be like if this is the y-axis, you can rotate the plane around it?
Yeah. There's lots of planes that are parallel to a given line. Yeah, absolutely. Yeah, the rules of parallel for line with line, not quite the same as the rules for parallel of a plane with a plane or a line with a plane. Yeah, it's all a little bit different in each sort of scenario. Yeah. Right. Okay. So let's see why this is true. This is a very easy argument. If there are no y's in the no y's in the equation, this is what that looks like. Keep in mind when you have an equation, you can just read what the normal vector is right off of the equation, right? The coefficients in the equation are the coordinates of a normal vector, which I can see right here. And now I can look at this 0 right there. That 0 tells me that, for example, this dot product with E2, right? E2 here is 0, 1, 0. And in dot E2 is 0. So this normal vector is perpendicular to the y-axis. And now I make a geometric appeal. If the normal vector is perpendicular to the y-axis, then the plane itself, as desired, the plane itself is parallel to the y-axis. And that's just a geometric appeal and gives us our result. How we doing? Everybody all right? Okay. Handy little fact. Comes up here and there. All right. Okay, let's do another sort of exercise here. So let's suppose that we have a couple of planes. And given those planes, we also have a point A. And what I want to do is I want to find the line that goes through that point A and that's parallel to both of the planes. And I geometric appeal again. I claim there's only one such line. Having to be parallel to both of those planes kind of dictates what the direction is that the line goes. And once then I also know what point it goes through, then again we're kind of done. Okay. Everybody on board? Okay. Further note, we want a parameterization of that line. So we're not looking for the symmetric equations for the line or any other sort of description. We want the parameterization. Okay, so how are we going to do this? Well, we're going to use what we already know, the normal vectors. I can read the normal vectors straight off of these coefficients, as usual. Notice I'm developing my picture as I go. Right? And let's see, we want a parameterization. We're saying, let's pause, remind ourselves, wait a minute, how do I parameterize something, a line that is? To parameterize, I need a point on the line, which I already have, sweet, right? But then I also need a vector parallel to the line. Okay, so this was given as, I've got two equations and I want to find a parameterization. And I've now kind of translated everything into sort of geometry, you might say, and now you might say, well, I've got these two normal vectors and I want to find this this direction vector that I have in dark green there. Right? And by the way, this is a good general strategy in solving these kinds of problems. When you're given algebra, infer the geometry and add that geometry to your picture. Right? And have everything given in the question and everything you can infer from the givens of the question represented in your picture. And so now strategically, again, I have these two vectors and I want to figure out how to use that to infer this. I have let's see here, the thing I'm trying to infer is, check it out, it needs to be perpendicular to both of them. V needs to be perpendicular to both N1 and N2. So I use the cross product. Again, the picture did the heavy lifting for me. Right? Does that make sense to everybody? Yep.
What would it mean if, we computed N1 cross product N2 and it happened that it was 0?
Oh, well, that would be very bad for the purposes of the question. Presumably neither of N1 or N2 is 0. I mean, then the equation of the plane would have been 0 equals hopefully 0. That's
it. Mean that they are dependent and they could be.
It exactly means that they are dependent. If you think about it, if you have two normal vectors that are dependent, that means they're parallel. And if they're parallel, that means the resulting planes are parallel. And now the question's not well posed, right? In other words, two parallel planes, there's lots of lines that are parallel to both of those planes. And so the question doesn't make sense. Yeah, right. All right. Okay, so the cross product did our work for us, and we're all good. All right. Now, I want to give you all a warning. There are some pitfalls with the kind of reasoning that I've just done a couple of examples of. I'm going to claim that I've done a couple of what I'm going to call transitivities of parallelness and perpendicularity. Let me walk you through specifically. So I argued that, the plane is perpendicular to its normal vector, and algebraically we showed that the normal vector was perpendicular to the y-axis, and then I inferred from that right? I transitively inferred a geometric relationship between the plane and the y-axis. There's a kind of a transitivity of sorts, if you will. Likewise here, I know that the normal vector is perpendicular to the plane, and the plane is parallel to the line, and then which is parallel to the v vector, and then I inferred, therefore, that the normal vector must be perpendicular to that vector. So, this is what I'm calling transitivities, the geometric relationship between two things, one of which has a geometric relationship to a third thing, and then inferring from that. So, the only warning I want to say here is just be careful. It is tempting to think that that these rules are, it's going to be kind of obvious. And if A is parallel to B and B is parallel to C, then doesn't it immediately follow that A is parallel to C? Slow down. Depends on what kind of objects you're talking about. If it's vectors only, then A parallel to B, B parallel to C, yes. But check this out. This vector is parallel to that plane, which itself is parallel to that other vector, right? And yet, I cannot conclude anything about whether V and W are parallel or perpendicular or anything. See what I'm saying there? So careful. Right? And I'm not going to go through and document all of the different possible combinations of vectors, planes, lines, parallel, perpendicular, perpendicular, parallel, perpendicular. There's too many. I couldn't possibly, and it's not even a good way to think about it anyway because you can't memorize such a long list of things. The best way to approach this, in my opinion, is just be careful, be aware of these kinds of pitfalls, and just make sure you don't write down something that doesn't make any sense, and let your geometric intuition be your guide. Yeah.
I know this works primarily because we can draw it out in part 3.
Yeah.
Will we ever, if we run into issues like this in higher dimensions when you can't imagine it?
Let me say I have no plans for doing such a thing. I don't want to tie my hands here, but let me just, I'm just going to leave it at I'm not a monster. And I'm not going to, create a problem that the satisfactory solution of which would require that students have good geometric intuition for 4 space. Right? No. It doesn't sound reasonable at all to me, right now. And hypothetically, if I think of some cool question that I want to put on an exam, I will think very carefully, about what I might need to tell you explicitly along those lines, because things do get weird. Yeah. Okay. All right. So another transitivity failure here that you can think through. P and Q are perpendicular. Q and R are perpendicular. P and R are no conclusion. Who knows about P and R? Okay. We'll probably just end it with this last observation here. If you want to parameterize a plane, parameterizing a plane is actually pretty straightforward. We need 2 things. We need to know a point in the plane, and we need to know a couple of vectors parallel to the plane. Now, notice this again defines a plane. If you have an A, you have a V and a W, there is only one plane that goes through that point that's parallel to these 2 vectors. Right? And, I can tell you something about every point in that plane. Then, every point in that plane can be obtained by starting at your A, by moving first Come on, I can do better than that. First, parallel to V, so some scalar multiple of V, and then from there, parallel to W, some scalar multiple of W. Right, so given the V and the W and the A, combining them like so allows me to get to any point in the plane. And so notice this gives me two parameters. So this is not a one-dimensional parameterization, right? We've got two separate parameters, S and T, that are needed to trace out this two-dimensional plane. So there you go. By the way, this may remind you of that exercise on the homework where you had to describe a parallelogram, right? This very similar geometric strategy in that exercise. And then a nice example here. I think this is going to be a great stopping point. So again, if you have 3 points given, A, B, C, you can pairwise subtract. That gives you two vectors parallel to the plane, and we're in business per the formula above. Everybody see that? Okay, all right. So we're going to draw the line right here because we're out of time, and we will pick up here on, are we meeting Monday, or is that Memorial Day? We are? Oh, Memorial Day is next week, is that right? Or the following?
Wait, let me check.
Yeah, I never can remember.
It's not this upcoming Monday, it's the Monday after.
Yeah, okay, so we are meeting Monday. Yeah, cool. All right, good deal. Okay,